apparently I already made this video, and apparently I didn't press record. So I'm going to do it again. And so I already actually cut out a piece of the thing that I want to redo. So what we're going to look at is RC circuits, which I've already looked at. But in this case, we're going to solve the voltage across the capacitor as a function of time with Python in a numerical calculation. And we're going to see how this could become a low-pass filter. Yeah, it's going to be great. Okay, so let's get started over here, and then we'll switch back over to Python. And am I recording? I am recording. It says I'm recording. Okay, so I think what happened was I pressed stop. Actually, I did record, but I just pressed stop. Okay, so switch over here, turn off that camera. Okay, so let's think about an RC circuit. So here I have a battery, and it has a voltage of EMF, which stands for electromotive force. And in this circuit, I have a switch, which I put right there. And when I close the switch, then I have a capacitor and a resistor, and current goes out of the battery. And when it gets to this capacitor, which we can think of as a parallel plate, it doesn't have to be a parallel plate, but think of it as a parallel plate, then, and we're at this conventional charge, which is the flow of positive charges, which is not actually that way, it doesn't matter, then these positive charges build up on one side of the plate. Those create an electric field that push positive charges off of the other plate, and so you end up with negative over there. So this charge on the plate Q is the amount of positive charge, and there's an equal and opposite negative charge on the other side of the plate. And then we have that resistor in there R. So the first thing to think about is the loop rule. The loop rule says that if I start at some point in a loop of a circuit and I make a complete loop and I add up all the voltages, then that total voltage change has to be equal to 0. That's the loop rule. So the other important thing is this definition of electric current. Electric current is the flow of charge. So if I take some small time interval delta t, then I can write the flow of charge as the change in charge over the change in time. Okay, so let's go ahead and write down. Oh, the other thing I need to know, let's write down the loop rule for this loop. I have EMF. I have the voltage across the capacitor, which is Q over C. I have the voltage across the resistor, which is IR. So with that, let's write down the loop rule. And I want to get to these are the theoretical equation. I'm actually not going to do this. I can do discharging too. For charging and discharging a capacitor, we're going to check this in Python, but we're not going to solve this. You would normally solve this by integrating, when we're not going to do that. Oh, finally down here, I am going to do a numerical calculation, and so with that, I need initial numerical values. So I'm going to use a battery, a 5-volt battery, a 100 ohm resistor, a 0.1 farad capacitor with 0 charge to start off with. Okay, so let's write down the loop rule, which I wrote right here and I cut it, you see. Okay, so if I go around this circuit starting from here, the first thing I get is going across the battery. That's the plus side of the battery, and that's the minus. So I'm going to have a positive change in potential of EMF. So let's say delta V loop equals 0 equals EMF. Okay. Now I'm going to come down here and I'm going to go across the capacitor, and I'm going from positive to negative. So the change in potential across this is going to be negative Q over C, right? Because it's a negative value, and so it has to be minus Q over C. And now I'm going with the direction of the current, and so the voltage drop across this is going to be minus IR. Okay, so there's my equation. Now I have EMF, that's a constant value. Q is the amount of charge on the capacitor, and then I have I. So both Q is going to change and I is going to change. But we need to see how they change in the same way, right? So I don't want to have I and Q. I want to instead put I equals delta Q over delta T, and then put that in right up here. So I have 0 equals EMF, oh, that's a bad one, minus Q over C, minus delta Q over delta T, R. Now, this is actually a differential equation, right? Because the current flow depends on this charge on the capacitor, but it's also how much the charge is changing. So here's how we're going to do this. I'm going to solve this for delta Q. So let's just do that. Let's solve this for delta Q. So I'm going to add this to both sides, and I get delta Q over delta T R equals EMF minus Q over C. Now I'm going to multiply by delta T over R, and I get delta Q equals delta T over R times EMF minus Q over C. So what I can do is, this change in charge depends on the charge. So it's actually a difficult situation. However, if delta T is small, let's say 0.01 seconds, then I can assume that the delta Q during that time interval, the change in charge that goes out of the capacitor, depends on the amount of charge on there, but that charge doesn't change. Right, so I'm going to cheat. This is cheating by assuming this is constant during that time interval. I can calculate delta Q. And then from that, I can say at the end of that time interval, Q2 is equal to Q1 minus delta Q. Right? Oh, no, I'm sorry, plus. I'm adding charge to it. So the charge I had at the beginning of the time interval, add that value that is found right there, and I'll get my new Q. And then I can do the same thing for time. T2 equals T1 plus delta T, which is that 0.01 seconds. And then I have a new Q. So I can go up here and calculate my new DQ. And I just repeat this over and over and over again. And this is a numerical calculation. And I could just do this, numerical calc. And this is actually the Euler method. And I could do this on paper by just doing these steps a whole bunch of times. If I want to do 1 second of plotting the voltage across the capacitor, then I would have to do this 100 times, because each time step is 0.01 seconds. So I'd have to have 100 of these loops, which you could totally do. But I don't want to do it. Do you want to do it? That's why I'm going to use a computer to do this. So we're going to use Python to do this calculation. And I'll admit that a lot of times I mess up the sign on this delta Q, but I think I got it right. So I'm going to calculate delta Q. I'm going to set up my initial conditions, calculate delta Q, calculate the new Q, calculate the time, and then I'm going to plot voltage across the capacitor as a function of time. Okay, so let's switch over here to the computer. Okay, so here, is that big enough? Let's see if that's big enough. There, maybe that's bigger. Okay, so let's start off with making a graph, because I want to plot the voltage as a function of time. So I'm going to say t graph equals graph. Graphing, I have a link down below for my tutorial on graphing in Python. So I can give it a title. Title equals a charging capacitor. Let's just say RC circuit, because I could do a whole bunch of different things. And let's say my X title is going to be time. Let's just call it T in seconds. And then my Y, and these are just labels. You could skip this part. And then my Y title is going to be equal to VC in volts. And then I'm going to do this. I'm going to make it smaller. The default graph just doesn't fit on here very well. So I'm going to say width equals 450. Height equals, let's say 300. Let's see how that looks. Okay, that just makes the actual graph. It doesn't plot things, so I need to plot things. Let's call this F1 equals G curve, color equals color.blue. And let's save it. RC, circuit, and stuff. I had another one, so I wanted it to have a different name. Okay, I don't like that. There. Okay, now I want it bigger again. No. Well, that's fine. Just make it like this. Okay, so now I need to enter my initial conditions. So I have EMF is 5, R is 100, C equals 0.1, Q equals 0. I need a starting value for the potential. So I mean for the charge on the capacitor. I'm looking over my initial conditions. I think that's it. Now I need time equals 0, dt equals 0.01. Now, is that a small enough time interval? I don't know. I'm just going to pick. I'm going to go with it. Let's just see what happens. Okay. So now we're going to say, let's run this for 10 seconds. So while t is less than 10 seconds, I like to start off with a time loop. So loops in Python start with this colon, and then everything that's tab indented is part of that loop. When you dedent out of the loop, then it's no longer in the loop. I like the time because I know if I add dt to my time, it's going to end, right? You don't want to get in an infinite loop. That's a bad thing. Okay, so the first thing I'm going to do is calculate my change in charge. So I'm going to say dq equals, now I'm just going to write down my equation. So I have dt times EMF minus q over c, all of that divided by r. I just typed that out straight from my equation that I had before. Now I'm going to use that to update q. So q equals q plus dq. So this in Python, this is not an algebraic equation. This does not say the q's cancel. This says take the value of the charge, add that dq that I just calculated, and make that the new charge. Okay, so it's a make equal to, not is equal to. So it makes it, it updates it. Now I can do the same thing for time, t equals t plus dt. And now I can calculate the voltage across the capacitor. Vc equals q over c. And I can plot that. F1 dot plot t vc. And I think that should work. Let's save it. And this is GlowScript v Python. Just in case you haven't seen this before, it's Python. It has a bunch of features in there, and the one that we're really using here is the graphing. It makes graphing really easy, and let's just run this. Okay, so that looks like it's working, right? So this is what we would expect. The capacitor's getting charge and charge, but it's not charging at the same rate, because the more charge I put on the capacitor, then the voltage across the resistor is smaller, so you have lower current. So let's go back over here and run this for, let's say, 30 seconds. And that's what we'd expect. Okay, now you'll notice it doesn't quite get to 5 volts, and it will never get to 5 volts. We could put the loop like this. While VC, which I don't have, VC equals, you can't put this in the loop if you don't already calculate it, is less than 0.95 times EMF, right? Because it's never going to get there, but it could get 95% of the way there. And let's run that. And there you go. So I think I'd go a little bit further. Let's go 0.99. And there you go. So it almost makes it there. And then you can look at the time. I could print out the time. I could print out the voltage and stuff like that. But what I want to do is to actually print the theoretical value. F2 equals G curve. Color equals color dot red. So that's my theoretical potential. And then we can go down here and say VTC, the theoretical value, is just going to be EMF times 1 minus the exponent of negative t divided by r, you got to put that in parentheses, r times c. And I can plot that too. F2 dot plot t VTC. Let's see what that looks like. Remember, the red is the theoretical. And they're right on top of each other. You can't even tell the difference. And that tells me my time interval actually is small enough, but let's just make it bigger. Let's make it really big, just so you can see a difference. And there you go. See, now you can sort of see that they're different. Wow, it just shows you how good this is. 8. There. So they are different if I get too big. But normally what you would do if you don't know the answer, what you could do is to decrease the time interval and see if you get a significant final result. So I could go down here and print the time. Print the time it takes to get to 95%. Print, let's just say t equals t seconds, and then see how much that changes as I change the time interval. So if I do this the first time, I get 46.03. Let's make it smaller. 001. And I get 46.05. So it really didn't change that much, right? But the 0.001 is obviously a better value. Okay, what if I do this? What if I have a discharging capacitor? I don't really need to do that much here. I could say the Q is not 0. It's going to be equal to let's say, what would be the initial charge? Well, if it's fully charged, let's say it's fully charged, then Q would be equal to C times EMF. So let's put this as C times EMF. So it's starting with an initial charge. And then the EMF is 0. Right? So now what's going to happen? I don't need to do anything else, actually, except to get rid of this plot, because that won't work anymore. Now I run this, and something bad happened. Oh, it didn't run. So it said while VC is greater than this. Let's run this for while VC is less than or greater than 0.1 volts. Let's just run that. It still didn't run. While it's greater than EMF, while VC is greater than 0.1. Let's do it for time. T less than 30. Oh, huh. Aha. So what I need to do here is to make a change. Right now I'm discharging the capacitor, so I need to actually, the current's going the opposite direction, so I need to decrease the amount of charge on the capacitor. That's what I need to do. No, what am I doing wrong? EMF is 0. No, it's already minus. Plus. So while T is less than 0, T VC equals Q over C. Q should be changing. Oh, I know why. Because I put 0 charge on there. I made that 0 and I made this. So let's say times 5. That's what I did wrong. There we go. I feel better now. And there's your discharging capacitor. Okay, now we're going to do something really cool. This is called a low-pass filter. Watch this. If I go back up here, is it still recording? Yes, it is. Okay. And I have EMF as 5. And let's put this at 0. And let's just run it to make sure everything's working again. No, it's not. R value. What did I do wrong? Oh, times. Okay, so that's back to charging. Okay, we're happy. Now, I have a constant voltage applied. That EMF is a constant value. But what if it's a oscillating value? So let's do this. Let's say omega equals 3 radians per second. Okay, and I say the EMF is now 5 times cosine omega times t. I guess I should put t equals 0 right here. So my battery is going to oscillate back and forth with this frequency for voltage. I mean, everything still works, right? In my small time interval, if that EMF is constant, then my equations still work. So let's just run this. And nothing changed. Wait, that's weird. EMF. Oh, that's why. Okay. So now down here, I also need to change the EMF. So I need to say EMF equals 5 times cosine omega times t, right? Because every time I update the time, I need to update the voltage across that battery. And there you go. Okay, so let's compare this voltage across the capacitor to the voltage of the battery, or the source. So let's make that other plot down there. I'm just going to use this FT, and let's use this T and EMF. And now run it. So remember, the red is the battery. So you'll see here that I have an oscillating voltage of 5 volts back and forth, and the output voltage for the capacitor across the capacitor is very, very, very small. And so this is, if I have this is like a high frequency source, I'm not getting much voltage out. What if I change this to a low frequency source? What if I change this to omega equals 0.3? And now I'll run it. Now you see I have a voltage, it's still going from 5 to -5, but now my output voltage is going from 1.2 to negative 1.2, so it's a lot bigger. So the smaller that omega of the source is, those frequencies pass through. And I could actually have a source with a whole bunch of different frequencies in it, and the lower frequencies are going to pass through more than the higher frequencies. Let's go back to something, let's do it this way, make it look a little bit better, for 100 seconds. And then let's do this 0.1. And there you can see I'm getting a very high output voltage, almost 3.5 for very low frequency. Of course, that depends on the value of the resistor, it depends on the value of the capacitor, but that is a low pass filter. But the key thing here is that we did this with just the normal RC circuit calculation. We didn't have to do anything magic except to change that actual voltage. We don't have to do AC circuits with reactance and stuff like that, which is still good, but it's also useful to see it this way too. Okay, so I'm still recording, checking right there, very happy. I'm going to leave you this code down below. I'll leave a link to my previous video on RC circuits where I derive the RC, the voltage equation, and the code, and graphing. And I'll see you guys later.